Hello everyone. Today I'm going to show you how we solve codeforces 1840G. It consists of two problems, G1 and G2, which have different difficulties there. I'll show you the code and the thoughts behind that, and demonstrate some calculation, some mathematical principles there. Okay, let's dive to the problem first. So for these two problem, they share the basic same configuration there. So basically, it means that it has a wheel that can spin freely, and this wheel is divided evenly into n sectors. So in each sectors, um, in these n sectors, there's a permutation of 1 to n implemented field into that sectors. Let's say 1, 2, 3, 4, 5, 6, 7, 6, 7, 8. So this is the 8 sectors. Of course, it might not be ordered. So basically, you have a pointer point to a given sectors, and it allows you to interact with the judge machine by sending plus a number or minus a number. So which means that you can rotate this wheel by n sectors and return the number on that sectors. And you are allowed to do 2023 queries in the G1, and you are allowed to do 1000 query in the G2, which is harder because you have um, less query times. So how do we do this one? So notice that this n is a number up to 10 to the power of 6, which leads to an algorithm called BSGS, which means baby step, giant step. So basically, how we do that is that we would increment, we would try to spin at a slow pace first, and then gigantic pace. Hopefully, we can iterate through a large query. For example, we would go step by step first and do this by 1000 times. And then we would spin 1000 times each time. And it's such that we are guaranteed to obtain with it the if we are not encounter a loop in the small baby step, then we are guaranteed to have a hit on the gigantic step because we are have visited the continuously 1000 sectors of these wheels. So let me show you the code here to the G1 problem so that you can have a. So each time we are trying to spin this one, we're output a plus number, which means rotate clockwise. We need rotate clockwise only in this problem. So plus a number, and then we do something, and then we read the output. So basically, this is some basic trick with input output system. Code start from here. We define the OPCNT as 1000, which means that we would do 1000 times for baby step and 1000 times for gigantic step. For baby step, notice that at the very first beginning, we are at the beginning we do not need to spin any time. The program, the judging machine would give us the current number of the sector we are at. So we read it and we continuously by spin this wheel one by one and see if we encounter a loop. If so, we just return true, which means that we're done already. Otherwise, we can't count the step at which we encounter this value. And then if we are not met a loop in the baby step, then we go gigantic step, and we're assured that we will meet a loop in the gigantic step because the n uh, is at most like a million. So with the same logic there, but notice that this time at the beginning of the gigantic step we don't read because we haven't spin yet. So um, so we read so we each time we spin by this time parameter which is 1000, and we're guaranteed to have meet the node we have met in the baby step, and then we return the true. Of course, we need to do some calculation to subtract the overlapped part there. Okay, that's for G1. So as you can see here, we're done. Get accepted. So for the G2, we have the same logic there, except that we are limited to 1000 query here. So we are still using the same BSGS step, trying to get a large range, but we won't divide this 1000 into 3 steps, each with, let's say, 333 steps. So the last two steps we still do BSGS, SGS, and by so we are guaranteed to detect any range less than 333 and times 333, which abruptly equal to one like 10,000, 100,000, yeah, 100,000. So um, so since we are only able to detect a length of such, then we have to try to guess how many sector at least we have in this wheel. In the previous problem, we noticed that we are guaranteed to find the answer as long as those numbers are unique. We doesn't require this number to be a permutation, which means that if, let's say, this 8 become 12, our algorithm still able to find the correct answer. That the size of this wheel is 8, because we either meet it in the baby step or in the gigantic step. But in the problem 2, we are going to exploit that attribute that the number of sectors are a permutation, which means that I spin this wheel randomly. If I encounter, let's say, 15, then the number of these sectors is at least 15. So it might have like larger number. So we spin the wheel randomly 333 times, and we take the maximum value, and we estimate that those we estimate that the number of sectors are at least that number, and then we're trying to fill in the gap by BSGS algorithm. So let me show you the code there. Basically the same logic there, but before we trying to do BSGS, we're doing some random choice. So notice that still we're at the beginning, we can directly read the indicator given by the programmer by the program. We don't have to output first. Then we trying to spin at a random speed and calculating the maximum value and then return this maximum value as our random choice. Thus, we know that the number of sectors in this wheel is at least span. Then we do BS baby step. Baby step is slightly different from the previous one. That first, at the beginning, we don't read because this first read has been done at the random step. And then after we done the baby step and we didn't find any loop, we are trying to jump this wheel by this span number, such that the the gigantic part of the wheel has been spin overed, and we can focus on the missing part there. So if we're lucky enough at this span, we would directly get the answer and we return the true. Otherwise, we return the false and continue the gigantic step there. Gigantic step remains the same, almost the same, except that we are taking an extra parameter span that calculates the gigantic the span value. We have spin over. So this is the code there, and we can see the submission here that this code get accepted. So and now I'm going to show you some mathematical proof that we are guaranteed to have this algorithm work. As I said before, we are taking some random gets from this wheel, and we take the maximum value. So, and our BSGS algorithm can only detect at most somewhere between 1 to the 5th power of wheel of gap that we hadn't matched. Then we want to know what's the possibility that falls between those range, right? So let's consider this. Let's jump into some mathematical field and see how that's going to work. Okay, so the problem can be stated as this. Forget about the wheel. Assume that we have an array of a permutation 1, 2, 3, 4, 5 with 5 elements. We are now taking 2 times, let's say 2 t to the 2. I want to know the maximum value, let's say equals 3. This is rather not this is a very this is rather not very convenient way to calculate or to reason about. But if we do another way, we can if we can calculate the maximum value that's less than 3, that's more easy to reason about. So there's 5 to the power of 2 times of ways of choosing 2 number randomly, and for maximum value less or equal than 3, there are 3 square way, which include 1, 1, 1, 2, 1, 3, etc. Notice that we're not guaranteed to have an exact number of maximum value there, but we have all the value less or equal than that.
Okay, same reason. What the possibility of max less or equal to 2? We have 2 to 5 of um, 2 square over 5 square. So we subtract those two, we get P max equal 3 equal to 5 to the power 5 square and 3 square minus 2 square. So such a way we can abstract as n to the t's power and this x to t's power minus x minus 1 to t's power.
That's how we do it abstractly. Okay, with that in mind,
I want to calculate, let's say p equal max equal um, let's say p max less or equal to n and great equal to, let's say, n minus 3. This should be p plus p minus 2 plus p. We can see from that um, we could see that those terms
are going to cancel each other.
and
Those terms are going to cancel each other, and those same for those terms.
so what we left is this one and this one equal to n to the t's power into t's power m minus 4 to the t's power. So
The, the possibility of we roll into the largest full number is this number. Is this number. So when we trying to abstract this four away, we get something like p largest d element equal to n to the t's power n to the t's power minus m minus d to the t's power. so. We are
And this can be done to the can be rewrite at this way.
so um, with this type of powers here,
Which lead us to this idea 1 minus
when we consider this inner part as the wholesome, it's pretty similar like the um, the limit where we have saw in the calculus, which when x goes to infinity, 1 minus x 1 over x to the x power is equal to um, natural log the reciprocal of natural log e. So um, so since we can only detect like 1 to the fifth power, plugging the number here, since we can most detect d can we're interested in the possibility that d falls into this range and n equal to this range, then we have something like 1 minus and we have the t equal to 333. So these are considered E, and this times T. And we can see that um, we can see that oh, I'm sorry. We can see that this number is very close to 1, since this number is very close to 0, 32 power there. So such that we are almost guaranteed um, to detect this number, to detect this range, detect this largest range there. So as the actually from the analysis we have before, we can see that this p is actually some kind of the possibility the possibility function distribution function is pretty much like some polynomial function there with uniformity, some uniform work to do. So yeah, so this n to the t's power is basically some, let's say this is a graph when you throw twice t equal 2. So you are guaranteed to have you are more likely to have a possibility that the max throw the maximum value you get from random throw are at some largest number there. So that's the source and mathematics behind the scene. That's it for today's video. Thanks for watching.